Universe's improbable constants. Imagine you're standing in front of a control panel for the entire universe. It's a vast machine, filled with dials, switches, and sliders, each one corresponding to a fundamental law of nature. One dial controls the strength of gravity. Another sets the mass of an electron. A third determines the energy of empty space itself. Now imagine that for this machine to produce anything at all, not just life, but even a single stable star or a simple atom, every single one of those dials has to be set to a value so precise, it's like a sliver of a hair's breadth on a ruler stretching across the entire galaxy. If you nudge any one of them, even by the tiniest, most infinitesimal amount, the entire machine either grinds to a halt, flies apart, or collapses into a singularity. The lights go out. The show's over before it even begins. This isn't a science fiction thought experiment. This is the staggering reality that physicists and cosmologists have been grappling with for decades. It's a concept known as the fine-tuning of the universe, and it presents one of the most profound and unsettling mysteries in all of science. It's the astounding observation that the fundamental constants of nature, these seemingly arbitrary numbers that underpin our physical reality, are set to values that fall within an incredibly, impossibly narrow range that allows for the existence of complex structures like galaxies, stars, planets, and ultimately, us. Let's take gravity, for instance. It feels familiar, strong, and constant, but in the grand scheme of cosmic forces, it's astonishingly weak. Yet, its exact strength is critical. If you were to increase the gravitational constant by just 1 part in 100,000 billion, a mere whisper of a change, the consequences would be catastrophic. The universe would have collapsed back on itself in a big crunch moments after the Big Bang. There would be no time for anything to form. Now, let's go the other way. What if you made gravity just a tiny fraction weaker? The result is equally bleak. The initial outward push of the Big Bang would have completely overwhelmed gravity's gentle pull. Matter would have dispersed so quickly and so thinly that it would never have had the chance to clump together. There would be no galaxies, no stars, no planets. Just an ever-expanding, cold, dark, and eternally boring soup of isolated hydrogen and helium atoms. A universe utterly devoid of structure or complexity. This is the cosmic tightrope we're walking. It's not just about setting the conditions for life. It's about setting the conditions for. Without stars, the universe is a dead end. Stars are the cosmic forges. They are the only places in the universe where elements heavier than hydrogen and helium are created. Every atom of carbon in your body, the oxygen you breathe, the iron in your blood, all of it was cooked up in the heart of a dying star and flung across the cosmos. No stars means no heavy elements. No heavy elements means no chemistry, no planets, no water, and certainly no biology. This is where the idea of the cosmic lottery comes in. The values of these fundamental constants appear to be the result of a random draw. But the odds of winning are so astronomically small that our minds can barely comprehend them. It's not like winning the Powerball, which has odds of about 1 in 292 million. It's not even like winning the Powerball every single day for the rest of your life. The odds are so much more ridiculous than that. The late astronomer Sir Fred Hoyle, who was initially a staunch atheist, was so shaken by these numbers that he famously said it was as if a super intellect has monkeyed with physics, as well with chemistry and biology. He compared the chances of our universe forming by random chance to the likelihood of a tornado sweeping through a junkyard and assembling a Boeing 747 from the scraps therein. Now, it's easy to dismiss this as an argument from ignorance. Maybe we just don't understand the underlying physics yet. Perhaps some future theory of everything will reveal that these constants to have the values they do, that they couldn't have been any different. But as it stands, our best and most complete theories of physics, like the Standard Model and general relativity, don't demand these specific values. The numbers appear to be arbitrary inputs, the foundational settings for our specific cosmic simulation. Physicists can and do run simulations where they tweak these values, and the results are consistently barren universes. This isn't just one or two lucky coincidences. It's a whole suite of them. It's a cascade of improbability. Scientists have identified a list of these cosmic constants that seem to have the winning numbers. They are the architectural pillars of our reality, the source code of the cosmos. And as we're about to see, each one tells the same story, that our existence is balanced on an impossibly fine knife's edge. We are the jackpot winners of a cosmic lottery we never even knew we were playing. So, let's take a closer look at the winning ticket. Let's examine the 6 most staggering numbers that prove our universe simply shouldn't exist.
6 cosmic, fine-tuned numbers we've established that our universe is the result of an unbelievably lucky draw in a cosmic lottery. Now, it's time to look at the winning numbers themselves. These aren't just abstract figures. They are the dials on the cosmic control panel, each one tuned to a value so precise that it boggles the mind. Let's break down 6 of the most critical. First up is the strong nuclear force. Think of it as the universe's superglue. It's the force that binds protons and neutrons together to form atomic nuclei. Its strength is represented by a number physicists call epsilon, which is about 0.007. If this number were just slightly different, the consequences would be universe-altering. If epsilon were, say, 0.006, a tiny decrease, protons and neutrons wouldn't be able to stick together. The only element that could exist would be hydrogen, with its single proton nucleus. A universe with only hydrogen means no chemistry, no complexity, no life. Now, what if epsilon were 0.08, a tiny bit stronger? The glue would be good. During the Big Bang, all the hydrogen in the universe would have rapidly fused into heavier elements. There would be no hydrogen left. This means no water, and more importantly, no long-lived stable stars like our Sun, which burn by fusing hydrogen for billions of years. Either way you tweak the dial, you get a dead universe. Our second number is one we've touched on, the force of gravity. It's the weakest of the 4 fundamental forces, but its exact value is paramount. It's about 10 to the 36th times weaker than the electromagnetic force. If it were even a little bit stronger, stars would burn through their fuel millions of times faster. They would be hotter, more massive, and would live for only a few thousand years, not nearly long enough for the slow process of evolution to get started on any orbiting planets. A stronger gravity also means a more dramatic cosmic collapse, as we mentioned. If it were weaker, we'd have no structure at all. The universe's existence depends on gravity being astonishingly, incomprehensibly weak compared to the other forces, but not weak. Third, we have the weak nuclear force. This force governs radioactive decay and plays a crucial role in the nuclear reactions inside stars. It's responsible for converting protons into neutrons and vice versa. The precise value of the weak force was essential for the amount of hydrogen and helium that came out of the Big Bang. More importantly, it's critical for supernova. When a massive star dies, it explodes in a supernova, scattering all the heavy elements it created into the cosmos. The shock wave of a supernova is a delicate process, powered by neutrinos interacting via the weak force. If the weak force were slightly different, these explosions would either fail, trapping all those life-giving elements inside a dead star, or be so inefficient that not enough material would be distributed. Our existence is owed to these perfectly calibrated stellar explosions. Our fourth number is the most famously, mind-blowingly fine-tuned of all, the cosmological constant, also known as lambda or dark energy. This is the intrinsic energy density of empty space itself, and it's causing the expansion of the universe to accelerate. Our best theories of physics predict a value for this constant that is enormous, but the value we actually observe is about 10 to the power of 120 times smaller. That's a 1 with 120 zeros after it. To get this number by chance is like throwing a dart from Earth and hitting a single specific atom on the far side of the observable universe. If the cosmological constant were even slightly larger, its repulsive force would have ripped the universe apart before galaxies could even form. If it were negative and just as small, the universe would have collapsed. The dial for this number isn't just on a razor's edge. It's on a sliver of a single atom at the very end of that razor. Fifth is the delicate balance of mass, specifically the electron to proton mass ratio. A proton is about 1,836 times more massive than an electron. Why that specific number? We don't know, but we know that if it were different, the universe would be unrecognizable. All of chemistry, the way atoms bond to form molecules, depends on this ratio. Change it, and the rules of chemistry change. Stable DNA molecules might be impossible. The very structure of stars and the formation of planets would be altered in catastrophic ways. Finally, our sixth number is the mass of the Higgs boson. The Higgs particle is associated with a universe-spanning energy field that gives fundamental particles their mass. Its own mass, discovered in 2012, turned out to be a fascinatingly precarious value. According to our models, its mass sits in an incredibly narrow, metastable range. If it were much heavier, the cosmic vacuum of space-time itself could become unstable, and our universe could spontaneously collapse at any moment, wiped out by a bubble of true vacuum expanding at the speed of light. Its value is just right to keep the universe stable for billions of years, but perhaps not forever. So, what do we do with this information? How do we explain this cosmic conspiracy of numbers that seems tailor-made for our existence? There are three main lines of thought. The first is simply incredible luck. We won the cosmic lottery. End of story. The anthropic principle states that, of course, we find ourselves in a universe with life-permitting constants, because if the constants were different, we wouldn't be here to observe them. It's a valid point, but for many scientists, it feels like giving up on finding a deeper explanation. The second, and a leading scientific hypothesis, is the multiverse. This theory suggests that our universe is just one of countless bubble universes, each with its own randomly set physical constants.
In this vast cosmic foam, the vast majority of universes are sterile and dead. But with an infinite or near infinite number of universes, it becomes statistically inevitable that a few, like ours, would happen to have the right combination of numbers for complexity and life to emerge. We are simply living in one of the lucky ones. The third possibility steps outside of science and into philosophy and theology: intelligent design. For some, the sheer improbability of these 6 numbers and many others points not to chance, but to a creator, a cosmic architect who deliberately set the dials to the exact values needed for a universe like ours. Whether the answer is luck, a multiverse, or a designer, the conclusion is the same. We are living on a knife's edge. The existence of our world, of our sun, of the atoms in our own bodies is contingent on a set of numbers so exquisitely and improbably balanced that it defies easy explanation. It's the greatest mystery of them all, a cosmic lottery ticket that we all hold just by being here.